For a simply supported beam that is subjected to two distributed loads W, we want to find the equation for the deflection and evaluate that deflection at point B and point D. The answer will of course depend on W, L, the elastic modulus, and the second moment of area of the beam. This is the first example for the bending deflection video, so if you haven't watched that one, make sure to check out the links in the description of this video. To find the equation of the deflection, usually known as the equation of the elastic curve, we'll use singularity functions. We'll begin with the distributed load equation, integrate the negative version of it to find the shear equation, integrate the shear to find the moment equation, and integrate 2 more times and divide by EI to find the slope and deflection equation respectively. The constants that arise from the first 2 integrals will depend on the external loads that affect the beam. So the first thing we have to do is find the reactions at A and C. Even though it's not necessary to transform distributed loads into point loads to draw a free body diagram of the beam, we'll do it in this first example so that the sum of moments and the sum of forces in the y direction are easier to write. The distributed load equation Wx has a minus W from 0 to L over 2 and another minus W from L to 3L over 2. Since the maximum value of x is 3L over 2, the last bracket will always be 0, so we don't need to keep that term. Integrating once and adding the external point loads, which are the reactions, as the integration constants, we find the function for the shear V. Notice that the location of the reactions matter. Integrating again, we find the function for the bending moment. And notice that I didn't add any integration constants, as there are no external couples affecting the beam. Integrating one more time and dividing by IE, we find the function for the slope of the beam. The integration constant C1 will be found using the boundary conditions on the deflection and slope of the beam. We integrate once more to find the deflection of the beam function. The 2 boundary conditions I'll use in this case are that the deflections at A and C are 0, since the beam cannot move up or down at those 2 points, which means that the deflection at 0 and the deflection at L are both 0. Using the first boundary condition, we find that C2 is equal to 0. And with the second boundary condition, we find that C1 is equal to minus 1 over 384 WL cubed. Substituting the values that we found for the reaction forces and now C1, we write the equation for the deflection of the beam. With this expression, we can substitute x for L over 2 to find the deflection at B, and substitute x by 3L over 2 to find the deflection at D. If you want to check one more example similar to this one, make sure to check out the link in the description below. Thanks for watching.